Alright, so in chapter 5 what we're going to be doing is looking at probabilities, but first what we have to talk about is what is randomness. So what random means is that something happens without a pattern. So some event occurs without a pattern. Okay, so when we're looking at probabilities, what we're going to be looking at first is theoretical probabilities. So what you can think of when we think of a theoretical probability is if we run an experiment, what can we expect to happen? Okay, so what these are called theoretical. Okay, so when you think of a theoretical probability, it's where you think about a probability but don't actually do anything. So for example, theoretically, if we flip a coin an infinite amount of times, theoretically it's going to come up heads 50% of the time and it'll come up tails the other 50% of the time. Okay, so however, it's impossible to do this an infinite amount of times, and even if we did it a million times, we're not guaranteed a 50-50 split. So, if we think about a regular deck of playing cards, what is the theoretical probability, or we'll just say probability, of pulling an ace from a deck of cards? Well, we have 4 aces out of 52 cards total, so we're not counting jokers. So the theoretical probability is 1 in 13. Remember, we haven't actually touched a deck of cards, we're just thinking theoretically what's the probability of seeing that. Now, empirical probabilities is when we do run an experiment. So this is when we actually do something or witness something. So when we talk about these, we talk about their relative frequencies or their probabilities. We either call them fractions or percentages. We use these when they're too complex for us to theorize about. So instead, we run experiments, or we might run what's called a simulation. So you can think of this as doing a computer simulation or doing something similar to the actual process that we're trying to learn about for the real life process. So for example, let's say I take a coin and I toss it 10 times, and what I see is that I see that 7 times it comes up heads and 3 times it comes up tails. Well, theoretically, it should have been 5 and 5, but the empirical probability is that I would expect 70% of the times it's going to be heads, and then 30% of the time it's going to be tails. So let's say, for example, we would use an empirical probability if we wanted to explore the probability that a stranger on the street returns a $5 bill that we dropped. Well, we can't say we have a 50-50 chance of getting our $5 bill back. So what we do is that we run this experiment, and we witness that out of 137 people we observed, 125 returned our bill. Then the empirical probability would be 125 out of 137 chance that we're going to give our $5 bill back. Alright, so whenever you're finding an empirical probability, right, remember you already did your simulation, what you're going to do is that you're going to write out the number of times the event that you're interested in occurred divided by the number of times you actually ran the simulation. Now, both probabilities have their place. So first, theoretical probabilities kind of give us an idea of what to expect. So they give us a basis. What empirical probabilities do is they allow us to do a couple of things. One thing that they allow us to do is that they allow us to test our theoretical probabilities. So sometimes our theoretical probabilities might be wrong, and we don't know that until we test them out multiple times, and we're like, hey, we're not seeing what we expected to see, maybe we've made a mistake somewhere. What they also allow us to do is they allow us to make predictions given complex systems. So, two examples that go along with these is one, let's say that we want to test out the theoretical probability for a certain board game and we don't know if our probability is correct or not. So what we could do is we could use an empirical probability by playing the game over and over in order, reviewing our findings and then seeing if they match. For the second one, making predictions on complex systems, this would be like trying to predict the weather. So there's so many things that go into what determines the weather for the day that we can look at days that have similar temperatures, pressure, wind, and make a good educated guess on what we think the weather's going to do for that day. Alright, now we're going to go into section 5.2, which is going to be talking about how to find these theoretical probabilities. So just using math. So first, note that probabilities can be expressed as a fraction, a decimal, or a percentage. Okay. So for example, if we want to know the probability that we toss a fair coin it comes up tails, we could either write it as 1 and 2, 0.5, or 50%. All of those are great. So what does it mean for an event to have a probability of 0? And what does it mean for an event to have a probability of 1? Well, a probability of 0 means it's never going to happen. Okay, so if something has a 0% probability, that means it's never going to happen. So for example, what's the probability that the sun doesn't rise tomorrow? It's a probability of 0. Now, if we have a probability and it equals 1, that means it must happen. So, what's the probability the sun will rise tomorrow? Well, that's 100%. It's definitely going to do that. Now, can a probability be less than 0 or greater than 1? The answer is no. So if you ever get a probability that's negative or a probability that's bigger than 1, that means that something's gone wrong and you need to go back and fix your answer. Now when we write probabilities, there's a certain notation we use. It's hard to write out every single time, like the probability of rolling a die and seeing a 5 is this. Probability of rolling a die and seeing a 7 is this. Okay, so instead what we write is P of the event equals, and then we write the probability. So, for example, if we want to write down the probability that we roll a 6-sided die and we roll a 2, we would write the probability of getting a 2 equals 1 in 6. Now this notation only makes sense if you have a context above, but it does help us out, especially if we're asking multiple questions using the same context. Now, the next question is, what is the probability that we roll a 4 or we do not roll a 4? So when we do an OR statement in mathematics, we're putting these two situations together. So if we roll a 4, we're happy, that's an outcome we want. If we don't roll a 4, well, we're still happy, that's still an outcome that we want. So the probability that we roll a 4 or not a 4, well, if I roll a 4 or if I don't roll a 4, that kind of covers every possibility. So that's going to give me a probability of 1 or 100%. When we say the probability that something happens or something does not occur, what we call that is we call that the complement. And we usually denote it by A to the C for complement. Another way you might see this in a different textbook or a different example is sometimes they'll write a tilde, that means not. So if you take the probability that something happens plus the probability it doesn't happen, well, you've covered all your bases. It's either going to happen or it's not going to happen. So when you add those together, it equals 1. This is helpful because sometimes to find a probability, it's easier to write down 1 minus probability it doesn't happen. So for example, by the way, you guys probably do this all the time and you don't even know it. So for example, if we use a complement to find the probability that we don't pull a 4 out of a deck of cards, well, the probability that we pull or we pull a not 4 out of a deck of cards, is going to be 1 minus probability that we do pull a 4 out of a deck of cards, which would be 1 minus 4 out of 52, which would give us 48 out of 52, which is 12 out of 13. A more realistic example of when we would do this would be, well, if the probability it's going to rain today is 22.5%, what's the probability it doesn't rain? Well, the probability that it doesn't rain, so the complement, which you could also write as doesn't rain, is going to be 1 minus the probability that it does rain, which would be 1 minus 0.225, okay, which would give us 77.5% chance that it will not rain. Alright, next up what we're going to do is we're going to talk about how to find these theoretical probabilities with equally likely outcomes. Okay, so when we talk about equally likely outcomes, we're going to be talking about things that have the same chance of happening. So think of a dice. Like every side of a dice has a 1 in 6 chance of showing. Each side of a coin has an equal 50-50 chance of showing, a deck of cards, etc. Okay, so we're not thinking of anything that's necessarily weighted. So first off, a sample space is a list that contains all possible outcomes. An event is any collection of outcomes in that sample space, and an event is not the same as an outcome. Okay, so let's look at an example. So let's say that we flip 3 coins simultaneously, and we want to write out that sample space. Okay, so first off, when we're doing this, there's a couple of different ways that you can write out the sample space. I like to use a tree. So first off, if we flip 1 coin, we can either get heads or tails. Now if we get heads on the first coin, that has 2 options of what we could get after. We can either get heads or tails. If we flip tails first, we can either then get heads or tails. After that, for the third coin, we can either get heads or tails, heads or tails, heads or tails, heads or tails. So what we do now is that we're going to follow each branch of the tree, and that will give us 1 outcome. So the first coin could be heads, heads, and heads. So that would give us heads, heads, heads for our 3 coins. Then we follow it to the other branch. I'll do that in a slightly different color. So we follow it to another branch, and that's going to give us another possibility. So we could have gotten, heads, heads, tails. So if we follow all of these branches down to their leaves or down to their endpoints, then we're going to get all the possible outcomes. So tails, heads, heads, tails, heads, tails, 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 heads, tails, tails, tails. So let's see, 1, 2, 3, 4, 5, 6, 7, 8. Great, so we have 8 total possible outcomes. Great, just like the hint said we should have. Now we want to circle the event where we have 2 or more heads. We flip and we have more than 2 heads. So that should actually say 2 or more heads. So let's see. I have 3 heads here. I have 2 heads here. 2 heads here. That doesn't count. 2 heads here. And that's it. So let's see. The probability that I get 2 heads or more is going to be, well, I have 8 possibilities total, and out of that I see my event 1, 2, 3, 4 times. So I have a 1 in 2 shot of getting 2 or more heads. So when you're finding the probability that you get, or if you're trying to find the probability of something and each thing has equally likely outcomes, what you're going to do is you're going to take the number of ways that outcome can occur, or the times you see the event, and divide it by the total number of outcomes, or you can also think of that as the size of your sample space. Alright, we're going to stop that here and we're going to pick it up on the next video since this one's already about 15 minutes long. So I will see you guys in just a second.